Welcome to this lecture on nonlinear systems. So, if you observe, most of the things that we have around are essentially, if you can represent it in terms of input and output, where input is some external stimulus and output is a quantity that you are interested in. Okay, so the relationship between this input and output. Sometimes satisfies the property of linearity, which we then classify the system to be as linear. For example, your spring mass damper system that you have always seen. But most of the systems that you would see around would possibly be not satisfying the property of linearity and hence making them non-linear systems, classified as non-linear systems. Okay, so even for the spring mass system, even though it is linear, in certain cases, depending on the nature of the spring, the linearity property might hold over small displacements. That is, the restoring force may be directly proportional to the displacement only over small displacements about the place of rest. However, over larger displacements, this restoring force may not be directly proportional to the displacement. It may have a non-linear dependence on the displacement itself. Okay, the human system that you see around, which runs a lot of complex processes, most of them can be uh, treated as nonlinear systems as well. As simple as the simple pendulum. If you look into the evolution of the motion of the simple pendulum here, it also is nonlinear system. It can be modeled as a nonlinear system. Okay, only over small ranges of oscillations or smaller amplitude of oscillations, one can see that the simple pendulum can be modeled as a linear system. Okay. Similarly, there are a lot of such examples that one can actually uh, think of. Okay, so in this series of lectures on nonlinear systems, we'll be considering dynamic systems. Okay, basically systems which can be expressed in terms of differential equations and algebraic equations, but more specifically we'll be dealing with those systems which can be expressed with a finite number of coupled first order differential equations. Okay, uh, so for example here there are n number of differential equations, so x1 dot x2 dot till xn dot. So x1 x2 xn are certain variables that are trying to describe how the system is evolving, and the rate of change of these variables x1 till xn, okay, they are dependent on uh, x1 till xn and the external input u1 till up. Okay, so we term these variables as the state variables, the xi's that you see, x1 till xn. We term all these n variables as the state variables of the system, and these, in some sense, represent the memory of the dynamical system. Basically, they talk of the past of this particular dynamical system in some sense. Okay, now so you have here n first order differential equations which are coupled with each other, and the other way of expressing them is in terms of vectorial differential equation. To be specific, we can represent this entire system in terms of one n dimensional first order vector differential equation. Okay, So putting all of them together, we get x dot to be equal to f of t x u. So x is the state vector that comprises of all the state variables. U is the input vector that comprises of all the p number of inputs that you have in hand. T is the variable that represents the time here, and the f is essentially the collection of all the functions f1 till fn. Okay, and we call this n-dimensional first order differential equation as the state equation for the dynamical system that we have in hand. Now for a system, sometimes we are interested in some particular variable which need to behave in a particular way, in a desired way, or there are certain variables which can be physically measured and we are interested in those variables. Okay, so such variables are essentially termed as the output of the system. Okay, because we are interested in monitoring them through measurements, direct measurements, or we are interested in making them behave in a desired way. Okay, so these are the outputs of the system, and the outputs dependency on the time, the state vector, and the input vector can also be a nonlinear relationship. Okay, so I am representing it, the output y as a function h. Okay, that maps t, x, and u to the output, and here there are q number of outputs here, and y is the output vector that we have in it, which is a q dimensional vector. Okay, and this equation is known as the output equation. Now the state equation together with the output equation is called as the state space representation or the state space model of the system. Why? Because the relationship between the input and the output is being expressed through the use of these state variables. Okay, so x dot equal to f of txu and y equal to h of txu are essentially the state space model of the system. Okay, now in most of the analysis that we'll see in this series of lecture, we'll be dealing with the unforced state equation, which is essentially of the form x dot equal to f of tx, wherein there won't be any explicit dependence of the state equation on the input. Okay, so you won't be explicitly present. Now that does not mean that the input is not present altogether. It's just that the input is either a explicit function of time or a explicit function of x or both. Okay, so when I say x dot equal to f of tx, that essentially means that if at all, if there is some input, it is either in the form of either explicit function of time or the state vector or both of them, and hence it has been replaced here. Okay, so we'll be considering it of considering models of this form x dot equal to f of tx or x dot equal to f of x when there is no explicit dependence on time throughout this series of lectures. So we'll be only dealing with such differential equation and hence such systems which are represented by these differential equations. Now, as I said, the dynamical systems evolution may have explicit dependence on time or may not have explicit dependence on time. Okay, so the state equation does not have explicit dependence on the time fact on t, the variable t or the time that we are considering here. Essentially, the state equation can be expressed as x dot equal to f of x, and such a system is said to be an autonomous system. Okay, so the system here is evolving on the basis of its initial state. So whatever initial state you consider at t equal to 0, on the basis of that the system will evolve. And if you want to see how the system evolves at a different instant of time, but you ensure that the initial state remains the same as you had considered at a previous instant of time. For example, let's say that you start a system today, start an autonomous system today at a certain initial condition, let's say alpha. Okay, and you check how the system is evolving. Now suppose instead of starting today, you decide that you want to start the system, you want to see how the system is evolving tomorrow at tomorrow at the same time, and the only condition is you maintain the initial, you start at the same initial condition alpha. Okay, in both cases what you observe is in the later case, the evolution of x, if you compare it with the former case evolution of x, then they are just time shifted version of each other. Okay, so the evolution would not change, they are just basically you will see a time shift. So essentially autonomous systems are time invariant systems. Okay, if there is a explicit dependence on time, then such systems would come to known as not autonomous systems, because their evolution is directly being dictated by when the system, at what time a particular initial condition is maintained, and such systems are called time varying systems. Okay, now whether time varying or time invariant, for certain systems there may be some initial conditions where if the system starts, then the system will stay there for all forthcoming time instants. Okay, so if it starts at a particular initial condition, let's say x of t equal to 0 is some x star. Okay, so suppose you start there, and if the system continues to stay there at x star, the initial condition where you started, as time progresses, does not buzz, then what does it indicate? Then it indicates that x dot, or the rate at which the state vector is changing, is 0, because x, the state vector, is always equal to x star, it's not changing. Okay, and this brings us to something known as the equilibrium point. Okay, so if a system starts at a point x star and it continues to remain at the same x star, basically the state vector does not evolve, it remains constant there, it remains there, then x star is known as the equilibrium point of the system. Okay, and because of this nature, the rate of change of the state vector will be 0 at such points if evaluated, and it remains 0. Okay, now this translates for non-autonomous system that the right hand side of the differential equation, that is f of t x star, has to be 0 for all time instants. Okay, so you take x star and you keep on substituting for any value of t, we will see that f of t x star is going to be 0. So it has to be 0 for all time instants. And for autonomous systems, since there is no explicit dependence on time, f of x star has to be 0. Okay, so if you have system which is represented, whose state equation is given by x dot equal to f of x for autonomous system and x dot equal to f of t comma x for non-autonomous system, and if you are interested in identifying what the equilibrium point is for, or what the equilibrium points are for this particular system of interest, then you should check for those points where x dot is going to be 0. Basically where the state vector if starts will not evolve and will always stay there. Okay, so this will give us equilibrium points. Now these equilibrium points may be single, may be multiple. Okay, and these equilibrium points can also be classified as either isolated equilibrium points or a continuum of equilibrium points. Okay, also known as continuum of equilibrium. Now you have to note here, as I said, since we will be considering unforced state equations, that does not necessarily mean that input is not present. So input is either in explicit form, has explicit dependence on time or the state vector or both of them. So the equilibrium point essentially depends on what, on the input. Okay, for example, in a RLC circuit, if you connect, uh, let's say voltage source across this series RLC circuit, then the steady state that the RLC circuit achieves is essentially going to be the equilibrium point of the system. Okay, because that is where the system goes. And the system, if at all, was already at that state, then there would not have been any change in any of the factors under consideration, like the current or the voltage across the capacitor and current through the inductor and so on. Okay, now if you change, let's say that you have connected a 5 volt DC across the RLC circuit, so you have a steady state uh, operation that you have, and that is what is going to be the equilibrium point under this particular input. If you change the 5 volt to, let's say, 10 volt, okay, so the steady state values will change, which means the equilibrium point is also different. So if you choose an input signal, then the equilibrium point is calculated under the influence of this input signal. Okay, for a different input signal, you will get a different equilibrium point. In some cases, we would like to know that in the absence of input altogether, what where would the equilibrium points of the system be? Okay, so in such cases, what you do is you just set u equal to 0, and then you have a system where there is no input, and you can compute the equilibrium point by equating x dot to be equal to 0. Okay, now this in general is I mean, whatever we discussed in general is true for whether it's a linear system or a non-linear system. Now, when we talk of linear systems, you would have already seen this particular structure where x dot equal to ATX plus BTU and y equal to CTX plus DTU. The general representation of a state space representation of a linear system, where if AT, BT, CT, or DT, any of these is time varying, then you have a linear time varying system. If all the system matrices A, B, C, D are constants, then you have a linear time invariant system. And it can be observed that such systems input output relationship always satisfies the linearity property, and hence they are called as the linear systems. But if the linearity property, in case you have a relationship, so what you have here is this essentially of this form, right? So x dot equal to f and y equal to h. With this equations, if the input output relationship is linear, then you have a linear system. If the input output relationship is non-linear, does not satisfy the linearity property, then you have a non-linear system. Any system input output relationship, if it does not satisfy the linearity property, you have a non-linear system in hand. Okay, now this is one property that distinguishes nonlinear systems from linear systems, that they do not satisfy the linearity property. But apart from them, there are other peculiar properties that can be found possibly in certain nonlinear systems, but definitely cannot be associated with a linear system. So we'll discuss three of them in the subsequent lecture briefly, because they are of interest to us. And these are the three properties which are basically something like a linear system can never have, but there can be nonlinear systems which may have this property. I'm not saying all nonlinear systems will have this property. You can find nonlinear systems that can have one of this property or most of these properties, but you cannot find a linear system that can have one of these properties. Linear systems cannot have. So what are these properties that we are going to see? One is finite escape time, which means the system can blow up in a finite time. Second is existence of multiple isolated equilibrium points. So you can have equilibrium points lying here and there in the space. So you can have multiple equilibrium points, and they may not be um, a continuous set altogether. And the third is the existence of something known as a limit cycles. So we'll discuss them in subsequent lectures. However, I suggest that you look up onto the literature that we have, the reference materials that I've suggested, and other reference materials that you can find out, and see what all other properties are there that a nonlinear system may possess, but the linear system will not possess, and thus distinguishing a nonlinear system from a linear system. So we'll stop here. Thank you.